This time on our global roundup of incredible engineering calamities. An apartment block that resisted demolition.
What a disaster!
A once thriving mining town now lies abandoned.
It became clear that this was no place that people should be living.
An engineering mix-up derails a new bus route.
How did they manage to get this so wrong?
And a global fail that's knocking the wind out of green energy.
The tips of those blades are traveling at supersonic speeds, so friction becomes an issue.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings. These are the engineering catastrophes that only an expert can hope to fix. As engineers push the boundaries of materials and design,
we have a space station in orbit, but it's crippled.
Every measurement is checked and double-checked with millimeter precision. But sometimes older constructions hold surprises that no one saw coming.
If it did actually fail and flood this area, those people would have been washed away.
Like this catastrophe in England, with a building that refused to budge.
A demolition like this, you've got to get it right first time.
An engineering fail that became the talk of the town.
I think at that point, there were a lot of concerned residents.
In the mid-20th century, Britain's population was booming. In crowded cities, planners found a new solution to create residential space.
Instead of building more houses and building out, they built up.
Concrete apartment buildings sprung up across the nation. With their views across towns and cities, they proved a hit.
At the time, these were a modern solution to the post-war population boom.
But decades later, many of these giant constructions were becoming worn out, and it was closing time. As demolition expert James Bibby knows only too well, bringing these solid concrete towers down is no easy job.
We demolished buildings in major cities that were built in the 60s. These were typically built by concrete methods. They want concrete beams and concrete floors. It's been built with a high density concrete and it's heavily engineered. It's just hard as nails.
In 2016, two 50-year-old apartment blocks in the Seaforth area of Liverpool were earmarked for demolition: Churchill and Montgomery House. Journalist Elaine Wilcox followed the story.
So the story I was covering was an area where there was going to be some major redevelopment, getting rid of the old 70s tower blocks and creating green space, new housing, new places for people to go. When we arrived, we were struck by just how close they were. These were enormous tower blocks, and they were surrounded by houses, very, very close.
The 15-story towers were surrounded by residential streets. Rather than a slow, piece-by-piece demolition, contractors opted to knock the towers down with a controlled explosion. Noisy and dusty, but quick.
When an explosive demolition works well, they're great. They can take down massive structures in no time at all.
With explosive demolition, charges are placed at strategic points within the building, from the central supports to the foundation.
On a concrete tower block, the stair core is typically the strongest part of the building, so we must ensure that we blow that stair core so that it fails. We'll blow 2 to 4 floors as well, so they will blow milliseconds apart, and then you'll blow the stair core with it.
The trick to a successful explosive demolition is getting the building to collapse in on itself rather than exploding outwards. So you put charges around the building and they then go off and weaken the concrete. And then what happens is the floors sort of concertina into each other until the whole thing is collapsed.
Although highly regulated, explosive demolition still comes with risks, including flying debris. So in Seaforth, the local area was evacuated. In theory, once the dust settled, residents would move back home.
So people were gathered, they were waiting, they had their cameras at the ready at the allotted time. Big noise, big explosion. And the 2 tower blocks just stood there, nothing happened.
Things had clearly not gone to plan. But as they say, if you first don't succeed, you just try again.
A few hours later, the demolition crew gave it another go.
Suddenly, there was a real rumble, a lot of noise, and Churchill Tower, that was standing here, that came down. But then they looked at the other tower block, and that was still standing.
Churchill House was now a pile of rubble. But although weakened by the explosions, Montgomery House was still standing. Until the tower was demolished, hundreds of residents, including Jake Curtin, weren't going home that night.
I think what was scary was the fact that nobody actually knew what was going on at the time. They were telling us they were going to pull it down. They were telling us they were going to do another explosion. Everyone was concerned. You know, my house is right next to it. Is it going to crush it? What's going to happen?
Engineers had to work out what had gone wrong and come up with a plan to bring it down. One small problem: they couldn't go inside the building to inspect it.
After 2 failed attempts, the structure was actually weakened and it could have collapsed at any time. The demolition team couldn't have got any sleep.
The next morning, the tower block was still standing. Engineers came up with a very simple plan to bring it down.
Having already tried to demolish the building twice, it was now too unstable for people to go in and prime the place with more explosives. So what they had to do was put cables around the base of the building and just use giant heavy machinery to pull it over.
Everyone was hoping for better luck the third time around.
Oh, no way! What a disaster!
The wire had only managed to pull the corner of the tower down, and now the building was even more unstable.
You think that you've got these plans, they know exactly what they're doing, the professionals. Why can't they bring this blowing building down? It was unbelievable, and to sit here and watch it unfolding in front of me was something else. It was crazy. You think it would just be boom, done, and that was it. And I think that's what everybody else thought as well.
The contractors were in the eye of the storm here. We spoke to them. They eventually did some interviews, and you can tell they were trying to be reassuring, to reassure residents, but they looked in shock themselves. Their body language, their appearance, they didn't know what was happening.
As a health and safety report later concluded, the engineering team had properly prepared for the demolition, as proven when Churchill Tower came down. But they later discovered that both towers were reinforced in a way that wasn't on any official plans. They just got lucky with the first tower. Montgomery Tower, however, resisted the explosions thanks to some small, undetected metal pipes.
We understand the reason why it failed was because there was these huge concrete columns and they had these steel rods inside, and that's what kept the building standing despite the explosion, the explosion, the explosion.
Concrete is strong when it's compressed, but it's much weaker under tension. So in large buildings, concrete is normally reinforced with steel bars called rebar.
Montgomery Tower was held up by 12 concrete columns. Deep inside each were a number of 10-centimeter long steel pipes, each about 2 centimeters thick, filled with concrete.
It turns out that pipes just about this thick could have been responsible for the failures.
Information on the short sections of pipe was missing from the tower's official paperwork. So contractors had not factored it in when drawing up the demolition plans. Now, only one option remained. Call in a specialist piece of machinery called a high reach. These supersized, custom-built excavators are used worldwide to bring large buildings down, slowly but safely.
It is the largest piece of plant that a demolition contractor will use. It reaches up to, typically somewhere between 7 and 20 stories. Its nickname is the long arm. It's absolutely massive.
A high reach has a powerful diesel engine, which pumps hydraulic fluids to raise the massive arm. A separate hydraulic system powers the giant shears, giving them huge strength for cutting and crushing with extreme precision. The operator is protected by reinforced glass with a series of cameras to help guide the arm as the building is brought down chunk by chunk. In Seaforth, the day after the failure, the team call in the tallest high reach in Europe, Goliath. With Goliath in action, residents had to stay clear for another 3 days, until finally, Montgomery House was safely down.
A week later, took many days, the buildings were down, and it's the start of the regeneration and hopefully, something positive here in the future.
Construction disasters can strike out of the blue, without warning. But some have been going on for so long, you can't help but wonder how things got so bad. For this catastrophe, it's off to Oklahoma and a decades-long engineering nightmare.
Looking back, this is just a smash and grab on the landscape.
This place has been described as one of the dirtiest places in America.
The seeds of disaster were sown a century ago, but it was only decades later that the true danger to this town was fully revealed.
This place is not only completely desolate, it's deadly.
The Tri-State Mining District straddles the borders of Oklahoma, Kansas, and Missouri. For more than a century, it was one of the world's most productive iron and zinc mining regions. At its heart, the town of Pitcher, Oklahoma.
Pitcher was your typical American town, baseball, apple pie, and hot dogs.
Although it's now abandoned, a little over a decade ago, Pitcher was full of life. John Sparkman's family lived here for generations.
This was my home in Pitcher, Oklahoma at 437 South Connell Avenue. And I grew up here having Sunday dinners here, family gatherings, birthdays, all the things like that that a normal family would have.
Phyllis and Greg Cruzen grew up and raised their family here.
We didn't even lock our doors.
Yeah, man.
Because if your neighbor needed you, they just came over and knocked, and sometimes knocked and came on in.
Yeah, lots of times they would just knock, or not even knock, and just walk in your door and say, hey, how's everybody doing in here tonight?
The boom began more than 100 years ago, when vast deposits of lead and zinc were discovered here. Journalist Wally Kennedy explains.
The mining in this area started in about 1918. And the reason why it came here is because this ground contained very high concentrations of lead and zinc ore compared to what existed in Missouri.
Lead and zinc were vital in every walk of life, from pots and pans to wartime ammunition. The metals are scattered within vast seams of less valuable but very solid rock called ore. Miners used dynamite to blast out the ore, creating a massive network of tunnels and chambers. Around Pitcher, these so-called rooms and pillars ran about 60 meters below ground. Miners had to extract 17 tons of ore to get just 1 ton of metal. Pumps worked constantly to remove groundwater, keeping the mines dry. When active, more than 160 million tons of ore were mined, producing less than 10 million tons of the valuable lead and zinc. The leftover waste, or mine tailings, were dumped in massive mounds around the town, known locally as chat piles.
We used to live on the south end of town, and people would come in and pull beside the road and want to know what type of mountains these were, what was the name of the mountain range. And we would laugh and just tell them, say, those aren't mountains, those are just chat piles.
The mines operated for 5 decades, producing metal worth billions of dollars. At its peak, more than 10,000 men worked the mines. The lead they produced was vital to America's war machine. But by the 1960s, Pitcher's mining boom had come to an end. The lead and zinc ore was all but gone. Operations were shut down, and the mining companies left town. That should have been the end of the story, but the decades of mining had set in motion a chain of disasters, which would only become apparent years later. As the mines closed, there was no longer a need to keep the tunnels dry. The water pumps were removed, and the vast underground network began to flood. Toxins made their way into the local waterways. Craig Creeman works with the Environmental Protection Agency to monitor the ongoing problem.
The mine waters are coming up. I think it's about almost 900 liters per minute, or 250 gallons a minute that are coming out of these points of discharge. You know, they had millions and millions of gallons of water that took over 10 years, from about 1970 to almost 1980, to basically get itself up to the top of the mine workings. And that's what this was. It was mine-influenced water, upwelling, orange-colored water coming out of the ground.
Tar Creek, which is just half mile back to our west from here, was flowing orange because a lot of water was bubbling up out of the ground, out of the mines, and flooding the water system.
But contaminated water was only one lingering issue from the mining days. Something equally dangerous had been part of life in Pitcher for decades. More than 100 million tons of waste material towering over the town, the chat piles. Despite being processed, they still contain dangerous levels of both zinc and lead, which poses major health risks.
We've had lead around for years in pipes, in paint, in fuel. For a long time, people have known that it's been toxic, but it was just too useful to give up on.
5 decades later, with lead being the main threat, the EPA still monitors the toxicity of the chat.
Right away, zinc's 1,500 parts per million, which our remedial goal for zinc's 1,100. And lead's at rated about 500, which is our remedial goal. But if you dig your heel into it, you can start seeing a lot of that finer stuff below it. So when I do that, but already the lead's at 850 parts per million and zinc's 5,500.
Although the chat had been here for decades, the full risk from the lead only started to hit home in the 1970s.
Lead primarily is the big human risk driver because of its neurological effects it has, particularly in children. So here in Pitcher, as a lot of these kids were growing up and exposing themselves to this chat, and sometimes the kids would ingest it, stick their hands in their mouth. 5,000 parts per million lead, or even 500 parts per million lead, that's not good for children.
By the 80s, the impact of Pitcher's chat piles on local residents started to become increasingly apparent.
Many of the people who lived here had medical problems. Their children had learning disabilities or some sort of hypertension. Adults had high blood pressure, and there were just a vast number of illnesses.
In 1983, the EPA declared Pitcher part of the Tar Creek Superfund, official recognition that the levels of lead were dangerous to its residents. Cleanup efforts began, which continue to this day. But below ground, there was yet another threat to the town, an unfolding catastrophe caused by the decades of tunneling.
This ground is very unstable. You know, it could cave in at any time.
The ground beneath Pitcher is riddled with more than 500 kilometers of mine tunnels and chambers, some 30 meters high. Sudden subsidence has been a problem since mining began in the early 20th century. In places, the entire surface disintegrated, forming sinkholes. But the extent of the problem was only officially investigated in 2004. The U.S. Army Corps of Engineers was called in to survey the area. 2 years later, they revealed that 86% of Pitcher's buildings were now at risk of collapse. Pitcher had long been a bustling mining town. But the decades of extracting lead and zinc was now destroying it. With contaminated water, hills of toxic waste, and unstable ground, the solution to this crisis was drastic. In 2006, the U.S. government offered to buy the homes of residents with children so they could relocate.
In the neighborhood that I lived in was just awesome. I mean, everybody, we knew everybody. We took care of each other's kids. My best friend lived behind me, and their kids tested positive for lead, and so they were one of the first to move out. And so it was kind of sad. It was like breaking up a big family.
Realizing the danger, other residents gradually abandoned the town. Pitcher's fate seemed sealed in 2008 when a devastating tornado hit with winds of 270 kilometers an hour. More than 100 buildings were destroyed, with 6 fatalities. By 2010, just 20 residents remained, refusing to leave their hometown. The EPA has officially declared the region uninhabitable. Efforts to mitigate contamination to water have been ongoing for nearly 4 decades.
So what you see here is the Mare Ranch passive treatment system. Throughout here, these different individual cells are passively treating. They don't need any kind of mechanicals, but they're just passively flowing under gravity, you know, down to a point where it discharges out these cells. And here we're at the end of it, and I mean, it's clean water.
Above ground, contamination is also being cleared.
These chat piles are going to have to be removed, but it's going to take a long time for them to do that because there's so much here.
Thousands of tons of chat piles have been removed, used to build roads, sealing the toxins safely out of harm's way. But the decontamination will take decades.
While I hated to see the town go away, I'm glad that children will not grow up in this environment anymore.
With no clever engineering fix, all they can do is look to the federal government for help.
Over the next 20 years, the government's going to spend $178 million on this site, and it's going to be a long time before Pitcher is going to be safe again.
For me, personally, it became clear that this was no place that people should be living.
While the cleanup continues, Pitcher stands as a reminder that engineers and officials must learn from the mistakes of the past.
It's incredible to think that this whole thriving community is now gone.
What built the town, I guess, is also what tore it down at the end. You know, the lead mine had built it, and what gave birth to it also killed it.
Engineering projects come in all shapes and sizes. Some cost billions, with no promise of making anything back. So if you think you're getting something for free, there's always a catch. Like this engineering fail that's hitting a global industry.
Wind turbines are meant to be the future of electricity.
In the drive for renewable energy, engineers underestimated Mother Nature.
We're talking about waves, salt water, strong wind energy. All of those combining is an issue.
This problem has got engineers in a spin.
In the 1980s, engineers were looking for alternatives to fossil fuels. One obvious solution was to tap into an age-old source of power.
We've been using wind power for centuries. This is just the modern version.
Nature is providing an unlimited free source of energy. All we have to do is harness it.
Harnessing the wind is, in theory, very easy.
Wind turbines are relatively simple. As the blades turn, they turn a generator, and that generator creates electricity.
With such basic principles, building the turbines should have been easy. But as engineers soon discovered, it took a complex mix of strength and aerodynamics.
The blades of a wind turbine may look simple, but they've been perfectly designed to harness as much power from the wind as possible.
First, to extract the maximum energy from the wind, the blades have to be at the right angle, known as pitch. Getting the pitch right is crucial, as Professor Lawrence Coates demonstrates.
Here we have a model wind turbine, the typical 3 blades. These are all flat. In a real turbine, you'd find as you go along the length, they'd twist to try and keep the angle of attack as close to optimum as possible. And what I'm aiming to show is the effect that the pitch of the blades, that's that orientation, can have on the actual power you get out. These are at 45 degrees. And let me just see what the voltage is. We're getting a reasonable amount of power out there.
Now the professor reduces the pitch from 45 degrees to 22.5, so the blade should catch more wind and generate more power.
So now that it's moving, the angle of attack is actually more close to optimum, and we're now getting significantly more power out.
In fact, reducing the pitch by 22 degrees doubles the power output. Optimal pitch also changes with airflow. The pitch of most wind turbines is adjusted automatically with wind speed, increasing or decreasing the angle to extract the maximum possible energy from the air. Working hard, exposed to the elements 24/7, the blades experience huge amounts of stress. Creating strong enough blades is demanding, even with high-tech materials, as turbine engineer Craig Siddons explains.
So most commonly, blades are made of glass fibre and epoxy solution. So what we see up the top here is the fibre, the glass fibre itself, that's not impregnated with epoxy. And this green colour here is the impregnated fibre. So this up here is obviously not impregnated. It's quite nasty to touch, so I had to put my gloves on to touch it. It can get into the skin, into your pores, and it's all together, it's quite nasty stuff. So the reason we use glass fibre epoxy is because for the strength it gives is for not much weight, so we can build blades that are very, very long and extract as much energy as possible from the wind.
3 decades ago, turbines began to spring up in remote, windy locations worldwide and started generating power, as energy consultant Simon Gray explains.
Behind me here today we have the Scroby Sands wind farm. This is one of the early wind farms, one of the first in fact to go offshore. So typically on the daylight today, as you can see, it's fairly windy. We're talking about this particular array here generating enough for about 40,000 homes. Overall, if we average it out across the year, I would say offshore wind and onshore wind is generating some 15 to 20% of the UK's energy.
As materials have become lighter and stronger, turbines have grown larger.
So if you imagine a building the size of the Gherkin in London, these are about the size of the towers. And if you think about the diameter of the blades, about the same size or slightly larger than the London Eye.
A single rotation of the largest turbine can power a house for a day. But if they're not turning, they're worthless.
Wind turbines aren't cheap. To make them pay, engineers have to keep them working constantly. Any downtime is extremely costly.
But only decades after the first wind farms were built, engineers worldwide discovered they had underestimated the power of Mother Nature.
Engineers are still finding teething problems with their original designs, and some of those problems are potentially huge.
Most concerning, these giants all over the planet were showing unexpected signs of aging caused by particles in the wind.
You might expect that giant turbine blades could easily cope with a bit of dust and rain, but being exposed 24/7, 365 days a year takes its toll.
Believe it or not, when engineers first installed wind turbines, they thought they would be pretty much maintenance-free. But they were wrong.
For years, engineers thought wind turbines would be the best way to harness green power. But these beasts have been under attack from Mother Nature. Engineers worldwide are seeing a drop in the turbine's power output. Inspections revealed that in many cases, the front of the blade, the leading edge, was suffering catastrophic damage. To keep the power flowing around the world, a solution is needed, and fast.
Any damage to the blade's leading edge means that it doesn't cut the air so smoothly. And that means the blade doesn't turn as quickly. Slower blade means less electricity generated.
So the leading edge here is very sensitive in terms of aerodynamics. Just a small defect can cause a defect in the lift that goes right the way down the blade. So it can have a huge impact on performance of the blade.
The problem comes down to the speed at which the turbines spin. It might look slow, but size is deceptive.
The blades are spinning at up to 180 miles per hour. That's almost 290 kilometers per hour.
At that speed, anything that hits the blades could cause massive damage, something these turbines off the coast of England were witnessing firsthand.
Well, you've got to remember that the middle of the southern North Sea is a fairly hostile environment. Effectively, we have sea spray, we have salt water, we have wind. All of these combine to cause major erosion on all sorts of structure, whether it be oil and gas or whether it be offshore wind. And particularly, the leading edge of the blade is particularly prone to this, given that it has that proximity to salt water and wind energy.
We might call it thin air, but the sky is full of impurities, from dust to lumps of frozen water. A simple example helps demonstrate what has happened on a large scale.
Imagine that you're a grain of sand, drop of water, possibly even a small hailstone, and you're moving along with the flow. And you're approaching the very front, or so-called leading edge of this blade. And in order to go over the top or underneath, you have to have a force applied to move you. But there's no time for that because the turbine blade is hurtling towards you at 150 miles an hour. And so you hit it. So if it's only one hailstone, it's not going to make much difference. But there's hundreds of them. And after about 2 or 3 years, these may create a larger hole. The wind will catch that and start to delaminate the turbine blade.
With blades so precisely shaped, delamination, or splitting open of the material layers, causes massive interruptions to airflow and loss of power.
It's amazing that these tiny pieces of dirt can cause such huge problems for these giant machines.
Renewable energy is the future, so engineers are working hard on solutions, from long-term, tougher materials to short-term fixes.
The solution here is relatively simple. Either the blades are coated in a strong protective paint, or an ultra-durable tape is applied to the leading edge.
The tape works like a Band-Aid and prevents further damage or even catastrophic failure of the blade.
It's quite simple to put on. Simply adhese it to the surface, some adhesive down here, pull it across, and then let it cure for a very short time. So it's quite simple for a technician to come in, learn how to put it onto the wind turbine. So we're hoping to put this on fairly quickly onto a number of offshore wind turbines in the field.
Not only can the tape fix a damaged blade, it can prevent it in the first place.
The blades can be protected when they're being built. It means they don't have to be stopped as often for costly and difficult maintenance. In this case, prevention is definitely better than the cure.
Now we know that turbine erosion is a problem. Let's hope that engineers tackle it as soon as possible and keep clean green energy coming thick and fast.
Engineering mix-ups can happen anywhere, from the smallest village to the greatest city.
They said, look, don't let the kids out. It's a major emergency.
And on the giant transportation projects that link them all. It's amazing how often things go wrong. First, it's off to Scotland and a famous bridge that was struggling to cope with its workload.
Nobody puts these bridges up and expects to get
only 50 years out of them.
The Fourth Road Bridge opened in 1964. At 2.5 kilometers, the engineering marvel was the longest suspension bridge in Europe. It was built to carry 4 million vehicles a year, but after just a few decades, it was carrying 6 times more traffic.
People did feel unsafe.
The lifespan of the bridge was a serious concern.
In 2004, as a precaution, engineers inspected the main cables. What they found was worrying. The bridge had lost 10% of its strength due to corroded strands inside the cables. The combined problems couldn't be ignored, so engineers looked for a solution. The plan? To dehumidify the cables with warm air. The fix succeeded, but the volume of modern traffic was now too great. The radical solution was to build a brand new bridge. And in 2017, the epic Queens Ferry Crossing opened. Now, the Fourth Road Bridge carries only emergency vehicles and public transport, but at least it's still standing. Next, we head to Germany for a very different transportation fail.
This is a road to nowhere.
Germany is famous for its network of high-speed roads, known as autobahns. In 2005, a new stretch of autobahn was built to connect the north coast. The route was a success, but after just 12 years, a 40-meter-long section collapsed. This part of Germany is a vast peat bog, a notoriously unstable foundation. For much of the Autobahn, engineers had driven huge piles through the peat into bedrock, building the road almost like a bridge. However, where it failed, they had tried an experimental system, using thousands of much smaller friction piles to support the road. In theory, these mini piles didn't have to be driven down to the bedrock, saving time and money. But in reality, the theory didn't work out so well. The peat was too moist, and the piles shifted out from under the road. A huge stretch of Autobahn completely collapsed.
It's always good to see engineers thinking outside the box, but this time their experiment didn't pay off.
To rebuild the damaged section of Autobahn, engineers are using a tried and tested solution. Large piles driven down to the bedrock will ensure a more successful road ahead. From roads to trains, and a transportation solution that gave one city a sinking feeling.
This is a nightmare scenario for a picture-perfect city.
Amsterdam is famous for its canals, culture, and architecture. But in 2008, some residents were shocked to find the ground sinking beneath their houses.
I heard just cracks. It was like the building was crying for pain.
Investigations revealed that ongoing construction on the Amsterdam metro system was responsible. Amsterdam sits on soft, wet ground, with millions of piles supporting the city. So the metro engineers used an ingenious box system to tunnel without destabilizing the piles and the buildings above. In 2008, some of these subterranean boxes cracked, allowing water and sand to pour in, leaving voids beneath the houses.
If water and sand leak into the tunnel, there's only one way for those houses to go: down.
Engineers repaired the boxes and put in new piles to stabilize the historic houses for good. Finally, in the summer of 2018, Amsterdam's metro was fully functioning. Meanwhile, in the UK, another very different public transport system was heading off track.
How did they manage to get this so wrong?
Worldwide, many cities use an underground metro to move people around. It's quick and efficient. but building them is expensive and disruptive. So for some smaller cities, it's not a viable option. In Bristol, England, heavy traffic drove city planners to seek a cheaper, more practical way to move people around. However, a small but crucial engineering mix-up failed to ease the congestion. Journalist Paul Barltrop knows all about the city's traffic woes.
Bristol's always had a really bad traffic problem, not least because it's a fairly well-to-do city, high levels of car ownership, and a geography which makes it quite hard to get lots of roads and lots of cars flowing smoothly around. There are rivers, there are hills, there are narrow city streets, and that's caused a lot of congestion over the years.
Bristol's engineering solution is a guided bus route called Metrobus. It works with sections of curb or rails that are installed on the sides of existing routes. The buses are equipped with guide wheels that make contact with the track when the vehicle enters a guided section. These effectively steer the bus like a tram on tires. In theory, with these segregated lanes, buses can run faster, more frequently, and more reliably than existing services. It's also much cheaper than building a metro or tram system. Transport engineer Bob Mingus explains.
Many cities just aren't dense enough in terms of the population to justify heavy rail or light rail systems. This is a system where you can have a trunk route of guided section and then buses fanning out into the countryside to visit villages or suburbs. So it's actually a much more flexible system, particularly in more low density situations that we tend to have in the UK.
Like the outskirts of Cambridge, where a guided bus system is already running successfully.
Cambridgeshire Guided Busway opened in August 2011. There had been scepticism before there'd be a bit of a white elephant, but within a few weeks we had to increase the service from buses every 10 minutes to buses every 7 minutes. It's tremendously helping Cambridge expand. It's helping people get to work, helping people get to college. Houses are being sold on the basis of the proximity to the guided busway, which shows people are prepared to pay that bit extra to be next to a rapid transit system.
But back in Bristol, on its multi-million-dollar Metrobus project, there was an engineering mix-up. The buses didn't fit.
What went wrong? If it was to technical standard, why didn't it fit?
In 2017, first tests ran on one of the most expensive stretches of the new track. They discovered that for 2.5 kilometers, the guide rails were too close together, meaning the buses couldn't drive through.
It's only, it's less than 3 kilometers worth of this, and it's only in certain places, but nonetheless, it's a bit of a mess.
There was only one fix for the problem.
There is going to have to be some relaying, some reworking of the guided busway, which is going to cost a lot of money and going to take a bit of time as well.
It took months and cost £200,000, but by late summer 2018, the guide tracks had been reinstalled at the correct width, and the route was up and running. The mix-up was a reminder for engineers that they should measure twice and cut just once. Construction calamities come in all shapes and sizes, from the destructive to the truly catastrophic, from the worldwide to the small scale. So long as we keep building, there will always be more engineering mistakes to fix.